Okay, now for resting potentials. Before we start talking about resting potential in its entirety, I think it's important to know about membrane potentials on a whole, right? So, membrane potential. So this usually speaks to the voltage of a membrane, right? Or the distribution of charge across a membrane. So remember when we're talking about, for example, the EMF of a cell, even though it's technically not a cell, well, it's a cell, but electrochemical cells, right? That's kind of what the neuron is kind of doing, right? The axon specifically kind of goes through, right? So there's going to be a difference in charge across a cell, right? So there's going to be a difference, right, in voltage, right? V for voltage across the cell, across the membrane. Right? So there's gonna be a difference in charge across the membrane. So really important. Now, how does this occur? Right? So if we look at a membrane, right? Let's say that this is a membrane and this is outside the neuron and this is inside the neuron. So inside, kind of like the axon here, right? Outside, here's the intermembrane space. So we know that. Note that we still have these, I would say no, these pumps, right? So it's due to really these different pumps, right? So let's have a look at it, right? These are sodium potassium pumps, right? So we're talking about sodium potassium pumps. So how, right, does this happen? How does charge get distributed across the membrane for it to be unequal, right? It's always about the sodium potassium pumps. All right, now let's see here what tends to happen with the input of ATP, right? So we're inputting ATP because this is active transfer. With the input of ATP, what generally happens here, right, is there's going to be some amount of movement, but we have to look at what type of movement is occurring, right? Sodium and potassium ions exist both outside and inside of the membrane. Keep that in mind. Both of them exist inside the membrane and outside the membrane. Remember that both of these ions, right? So let me write sodium and potassium, right? Both of these are positive ions. Gotta keep that in mind. Both of them are positive. So how does this difference in charge occurs? Well, with the input of ATP here by into the sodium potassium pump for active transport, this tends to pump sodium out, sodium ions out, and potassium ions in. But guess what? They're the same charge. But the thing that makes a difference is that there are 3 sodium ions being pumped out and 2 potassium ions being pumped in. Right? So that creates a difference in charge. That makes the outer membrane more positive. Right? So we're going to be having way more sodium than potassium inside the membrane. Note that sodium will still exist inside, but there's going to be more potassium, right, than sodium inside the membrane, because for every 3 sodium that goes out, 2 potassium comes in. But note now that this is actually amplified by the fact that potassium, right, so I could add this, right, let me add a page. Yeah, hold on, let me add a page here. All right, so this could be should be there. Okay, so this is gonna be amplified by the fact that potassium ions, right, are more permeable. Right? So they're more permeable, or I wouldn't say it like that. The membranes are more permeable to the potassium ions. So yeah, the membrane is more permeable to potassium ions, right? To potassium ions. So this means, right, that there's gonna be more potassium ions going actually out. So these are what we call our leaky channels. So this is what we call leaking. We call it leaking, right, because we notice that the potassium ions, right, move easily through the membrane, right? So these potassium ions are still going to be moving through. So watch this, right? We have 3 sodium ions, 3 positive charges being moved to the outside of the membrane, and 2 positive charges being moved in each time. Alright, so this is happening each time. Alright, so let me just show it here as well. 3 sodium ions, right, and comes in 2 potassium ions. But even though potassium ions are coming in, potassium ions are still leaking to the outside, so we're gonna have a way more, right, positive charge on the outside. So this translates to resting potential, where there's more positive charge on the outside than on, well, that looks weird, than on the inside. Right? So this is what resting potential speaks about. So this resting potential, though, now the potential inside the cell, right, is around negative 70 millivolts. Right? So these sodium potassium pumps creates this electrochemical gradient, right? So remember, this is an electrochemical gradient. Electrochemical gradient, right? So we have that there, where we're gonna have more positive charge on the outside than negative charge on the inside, and that's where we're going to get our negative 70 millivolts, right, for our resting potential. And this resting potential usually means, right, that when the neuron is at this rest, right, there are no impulses. Right? So no messages are being sent in. So there are no impulses. So generally, where there's no message, there's no electrical current going through, there's no action on the neuron, right? It stays at rest at around 70 millivolts, right? And this is because of the ion distribution, right, due to the sodium potassium pumps, right? I hope that was helpful in understanding resting potential.